Hi, today we're going to talk about the Nernst equation. So back when we were talking about free energy, we talked about the difference between free energy under standard conditions and free energy under non-standard conditions. And so you might remember this equation. Well, what we're going to do here is link this to cell potentials. So remember that delta G equals minus NFE. That was something that we just brought up in our last video. And then delta G naught, so delta G under standard conditions, is going to equal to minus NF E naught. So let's go ahead and plug those equivalencies into this equation, and we get this. Now obviously this is a hot mess, so what we're going to do is we're going to divide through by negative NF, and then what we get is the cell potential at any given point is equal to the standard cell potential, so that's the cell potential under standard conditions, minus RT over NF times the natural log of Q. And remember that Q is our reaction quotient, so this is linking concentrations as well as other things. This equation is called the Nernst equation. And what we're going to do today is just think about a couple of different ways we can apply this. Yes, the Nernst equation is something where you could just plug stuff in when you have the right numbers, but usually before you get to that point, there's a whole bunch of things you have to figure out before you can actually plug numbers into the Nernst equation. So first of all, you're going to need to write a balanced reaction and determine the number of electrons that are exchanged in the redox reaction. Now, in my last video, I kind of shortcutted and said, hey, as long as you can figure out the number of electrons that are exchanged, you're good. You don't actually need to write a balanced redox reaction. That is not true if you're using the Nernst equation, and I'll explain why in a later step. The second thing is you need to calculate the standard cell potential. What is your cell potential under standard conditions? And you're going to do that by looking at the table of standard reduction potentials. Third, make sure you have your temperature in Kelvin. Almost always you're going to be getting your temperatures in Celsius, so just make sure you've got the right temperature units. And then finally, you need to write that expression for Q. So you're going to have your mass action expression, and you're going to need to have your concentrations to plug in once you have the mass action expression. Now, where do you get that expression for Q? You're going to get it from your balanced redox reaction, and that's why you actually need to write out the balanced reaction in step 1. So there's a number of different questions that you can use the Nernst equation to answer. Here is one. Here, we're trying to figure out if a reaction is spontaneous under non-standard conditions. Now, if you look at this, the first thing you see is 25 Celsius, and you might say, hey, Robin, that is standard conditions, isn't it? How is this non-standard? Well, the answer is look at these concentrations. Remember that standard conditions include having everything at 1 molar or 1 atmosphere if you're doing a pressure-based Q. We don't have 1 molar concentrations, so we are not under standard conditions. So let's go ahead and make sure that we have all the things that we need before we actually get to plugging stuff into the Nernst equation. So the first thing we're going to do is we're going to write the balanced reaction and get the number of electrons that are exchanged. So it says that nickel 2+ is being reduced to solid nickel. That means our first half reaction is going to be a nickel half reaction, and we have to throw in 2 electrons to balance the charge. Again, if you don't remember how to balance redox reactions, I'm going to drop a link to the video down below in the description. So we have our reduction of nickel. What is reducing nickel? Solid cobalt. So cobalt is going to be oxidized. What is it oxidized to? Well, it gives us a concentration for cobalt 2+. So that implies that we're going to cobalt 2+. And then we have to add electrons to balance the charge. So here are our 2 half reactions. And you'll notice we have the same number of electrons in both of them, so we don't need to multiply anything. We're going to have 2 electrons exchanged. And our balanced reaction is going to look like this. We have aqueous nickel 2+ plus solid cobalt gives solid nickel and cobalt 2 plus aqueous. Now, in my videos, I've been a little sloppy about including state symbols, but in this particular case, it's going to be very important when we get to a subsequent step. So the next thing is to calculate the standard cell potential. And so what we're going to do is we're going to look at our reactions. We have our nickel being our reduction reaction, and we have our cobalt being our oxidation reaction. And so we can plug that into our equation for cell potential, and we're going to have negative 0.25, which is our reduction reaction nickel. And then the standard reduction potential for our oxidation reaction is negative 0.28. So we're going to have negative 0.25 minus negative 0.28. So that would turn into plus 0.28. And we get a cell potential of plus 0.03 volts. All right, holding on to the cell potential for later, let's make sure that we have our temperature in Kelvin. So we're just going to add 273.15 to our Celsius temperature to get 298.15 Kelvin. And then we need to find our Q expression and the value of that. And so remember, to get the mass action expression that's going to give us our Q value, we're going to put concentrations of products divided by concentrations of reactants, but we don't include anything whose concentration doesn't change, and that includes all solids. So this is why those state symbols were so important, because we have solid nickel and solid cobalt. So our Q value is just going to look like this. We have the concentration of cobalt 2 plus in the numerator and nickel 2 plus in the denominator. Basically, what we're going to do, let's plug in our 0.03 for our standard cell potential. R is going to be our gas constant, 8.314 joules per mole Kelvin. We've got our temperature. We've got our number of electrons exchanged, 2. And we have Faraday's constant, 96,500 coulombs per mole. And then the natural log of our Q, which is going to be our cobalt 2 plus divided by nickel 2 plus. So there's all that. You can see I've plugged in everything, including the concentrations of cobalt and nickel, 0.5 and 0.1. Just a quick note here, if you look at what happens with our units, you can see that we have moles canceling and kelvins canceling, and that leaves us with units of joules per coulomb, which is volts. And so we end up with 0.03 volts minus 0.02 volts, and that gives us a cell potential of 0.01 volts under these conditions. Now, is this spontaneous? It is, because anything that's greater than 0 is going to be spontaneous. So now we have another problem in which we're reacting iron 2 plus and oxygen, and we're getting iron 3 plus and water out. It's happening at 20 Celsius. We know it's an acidic solution, pH 2, and we're given an oxygen concentration. Now this time we've actually measured the cell potential using a voltmeter, and so we know the cell potential is 0.54 volts. And the question is, what do we have more of in the system? Do we have iron 2 plus or do we have more iron 3 plus? So this is the sort of thing that is useful if you're looking at, for example, an environmental system, and you're trying to figure out what is the predominant sort of iron in this system. Because sometimes you have bacteria that live on one sort of iron and not the other. We're just going to go through and double check to make sure we have all 4 of these things before we get into actually solving the Nernst equation. And so let's start with our balanced reaction. Our first half reaction is going to be turning iron 2 plus into iron 3 plus. We have to add an electron to balance the charge. And then we're going to use this reaction where oxygen reacts with H plus and electrons to form 2 waters. And if you're not sure what the balanced equation is, if you know that oxygen is turning into water, you can go look in your table of standard reduction potentials to find an appropriate half reaction. And so that is pretty easy to do if you're just scanning through and looking for stuff that includes oxygen. Now we want to put these together into a single balanced redox reaction, and to do that we need to have equal numbers of electrons. So we only have 1 electron on top and we've got 4 electrons in the second half reaction. So we're going to have to multiply that by 4 and then add things together, cancel stuff out, and we get the following balanced redox reaction. So we are exchanging 4 electrons here, and we're going to hold on to that number because that is the n in our Nernst equation. Next up, we're going to calculate the cell potential for this reaction. So which one is the oxidation and which one is the reduction? You'll know this because the reduction is always the one, first of all, that is written in the same order that it is in the table of standard reduction potentials, but it's also the one that always has the electrons on the left side of our double arrow. So in this case, oxygen is being reduced, iron is being oxidized. And so our standard cell potential is going to be the standard reduction potential of our reduction reaction, that's our oxygen, so 1.23, minus the cell potential of our oxidation reaction, which is our iron reaction, and that's going to be 1.23 minus 0.77. That gives us a standard cell potential of 0.46 volts. So we're done with our half reactions. I've moved those off the screen. What we're going to do now is we're going to make sure our temperature is in Kelvin. We're operating at 20 Celsius, which gives us a temperature of 293.15 Kelvin. Now we're going to find the Q expression. So for this, what we need to do is we need to basically put the concentrations of all our products, divide that by the concentrations of our waters. Don't forget that you have to raise things to powers if they have a coefficient that is something other than 1. If you look at our products, we have iron 3 plus, 4 of those, and we have 2 waters, but water is a pure liquid. We don't include it in our mass action expression. So our Q is going to look like this. We have iron 3 plus raised to the 4th divided by H plus to the 4th times iron 2 plus to the 4th times oxygen. Whew, that's a lot more complicated than the Q we had before. So now at this point we have everything we need. We're going to start plugging stuff into the Nernst equation, and this thing is such a monster I had to clear everything else off the screen. One thing that was in the original problem that I didn't put on the screen is that we measured the cell potential under non-standard conditions and we got 0.54 volts. And that equals 0.46 volts minus all this mess. And so you can see in the Q value over here, I have entered 0.009 for our O2 concentration. Our pH was pH 2, so that means our H plus concentration is 10 to the minus 2, so I put that in for H plus. Let's simplify this as much as possible. So now we're going to simplify that as much as possible. I have subtracted 0.46 from both sides. I've simplified the mess that is this big fraction over here next to the natural log. And then I simplified as much as possible the concentrations within those parentheses. Now let's simplify it further. We'll divide through by negative 0.01263. And we get negative 6.335 equals the natural log of our concentration mess. And now we want to get rid of the natural log, and so we're going to do e to both sides. So we have e to the negative 6.335 equals 23.13 times a ratio of our iron concentrations. That gives us 7.67 times 10 to the minus 5th equals the ratio of our iron concentrations. And remember, those iron concentrations are raised to the 4th power. We need to get rid of those exponents, so we're going to take the 4th root of this. And by the way, the easy way to do that on your calculator is just to do the square root twice. And we get that the ratio is 0.094. Going back to our original question, it asks, is there more iron 2 plus or iron 3 plus in the system? And so when you look at our ratio, you see a small number, and that means we have far less iron 3 plus in the system than we have iron 2 plus. The Nernst equation is very versatile. It helps us determine cell potentials under all sorts of non-standard conditions, and that helps us figure out whether reactions are spontaneous or not. I hope this was helpful, and I will see you again soon.